Hello and welcome. Today we'll be looking at the determination of the focal length of a converging lens using optical pins. We call this method no parallax method. No parallax method. So we'll look at why it's called the no parallax method. Right, we'll look at that. Okay, so first of all, the setup. We need a convex lens, optical pins, and a meter rule. And this is a diagrammatic expression of how the setup looks like, right? So from the object pin, the distance from the object pin to the lens is D. And then the distance from the search pin to the object P is given as L. Okay, so let's look at the setup. So this is how the setup looks like. This is how the setup looks like, right? This is the setup. This is the setup. So let's quickly look at how it is performed. Let's quickly look at how it is performed, right? So when you are starting, we only place, in the beginning, we only place the object pin. See, this is the object pin, right? We place this object pin. This one is the object pin. We can place the object pin on any point. So let's say 2, right? 2 centimeter. So it's on 2 centimeter. The middle, right? See the calibration. You see there is a line in the middle, right? So all the measurements will be taken from the middle, right? From the middle. So we place this on the 2 centimeter mark, the middle, right? Then we can use this screen to look for our image, right? To look for our image. So this is the first step, right? The next thing is to introduce the lens, right? Now, where do you introduce the lens? Because the method they gave us, the method that was given didn't tell us where we place the lens, right? The method didn't tell us. So where do we place the lens? Now, to know where to place the lens, we need to go back and then revise the properties of the converging lens, right? Some of the images that it gives. We know that the converging lens gives an inverted image. Okay, the converging lens gives an inverted image, right? It also gives a magnified image, right? It can also give us image that is same size as the object. You can also do that depending on the position that you place it, whether it's beyond the F or not, right? So we'll be using 2 of these properties here that will guide us to know where to place this lens. So the first that I'll be using is the invertedness. We should check whether the image that is passing through this lens is inverted or not, right? So first of all, from this side, right, we can check whether the image is inverted or not. So let's try and see if we can have a look at it. So when we look, when we look into the mirror, the lens, we can see the pin inverted, right? So that's the pin over there. You see the pin over there is inverted through the lens, right? So it's inverted. So that's the first property that we'll be looking at, whether it's inverted. Now, if it's inverted, we need to also position it at the point where it will be the same size as the object, right? So that's the object over there, right? Down the object. We need to check whether the image we are seeing through here, which is inverted, is the same size as the object. So we can just adjust this. We'll be adjusting this, right? Because when you bring it closer to you, it becomes magnified. When you bring it further away, it becomes magnified. You see, further away it becomes magnified. So we have to place it at a point where it's the same size as the object, right? So once we do that, then we mark that position, right? That's the position, right? Then the next thing is to introduce the search. The next thing is to introduce the search pin, right? So where do we also place the search pin? We also don't know, so we need to look at it. Now, this is where we introduce the no parallax method, right? We need to place the search pin. We need to place this search pin at a point where the head, the image, the inverted image, then the search pin will be coincidental, right? And then when you move your head this way and this way, they move together. When you move your head this way and this way, they move together, right? So that's what we'll be looking at. So we'll look through here, this end, right? We look through this end and check whether they are head on and then they move together, right? That's what we'll be looking at. Okay, so now this is the setup. We place the lens at the point where we get an inverted image of the object pin over there. The first pin over there, that's the object pin, which is the same size. The inverted image should be the same size as the object when we look through the lens, right? Then we introduce the search pin. Now when we introduce the search pin, we will see that the object pin will be seen launching like this, will be like this, inverted. Then the search pin will also be like this, right? So when you move your head, it should move together. So that's the no parallax position. Okay. Then we measure the distance. After that, we have to measure the distance from the object pin, right? We measure the distance from here to here, right? So from the middle to this middle, the distance between as our D, right? Then we measure the distance from our object pin to our search pin as our L, right? So let's look at the theory. Now let's look at the theory. So we know that. So let's look at the table first. So the table will be our D, centimeters, then our L in cm. Then we'll have L minus D, and then L minus D over D, right? It's in centimeters, right? So this is how the table will look like. Then we record the values, right? Now we'll be plotting D, right? We have to plot a graph of, we are plotting L minus D against L minus d over d. Now we know that L minus d equals to the image distance right. L minus d is the image distance. This is the image distance. And then our L equals to our object distance, right? Our L is our object distance, right? We are plotting this L minus d against L minus d over d. But L minus d is our image distance. And then our d, is d. And then d is our object distance, right? Now, from this means that if we are plotting this against this, right? If we are plotting this against this, it means that our L minus d will be here, and then the unit is in centimeters. Then our L minus d over d is in centimeters as well, right? Like this, like something like this, right? And then this component means that L minus d over d will be the same as, because we said this is our image distance and this is our object distance, right? And then we know that in optics, our image distance over object distance is the same as V on U, right? And then this V on U represents something. V on U, M equals to V on U, right? So M is the magnification. So magnification equals to the image distance over the object distance, right? So we'll be plotting a graph of the image distance, right, against the magnification. So this is also the same as the magnification, right? This is the same as the S component is the same as the magnification. Okay, so we are plotting the image distance against the magnification. So this is also the same as image distance, right? This can be the same as V on M. Do you agree? Because this is image distance, which is indicated as V, and then M is the magnification. So this, we can say that L minus D equals to U, and then L minus D on D equals to M. So we are plotting this against this. So that's where we employ this equation. We employ this equation, M P on F minus 1. So this is the equation that we'll be using for this no parallax experiment. No parallax experiment, right? We'll be using this equation. Now, where from this, we know that magnification is also equals to, is this, but it's also equals to 1 on F, right? Do you agree? So magnification is also equals to 1 on F, right? Now, if magnification equals 1 on F, and then in here, right, what we did here, we said we are plotting this and this, right? We are plotting this and this. So we are plotting this as ordinate, right? We are plotting this as ordinate. V, which is the image distance, as ordinate, and then magnification as the abscissor. It means that we can use this to depict the equation for this particular experiment, right? So that we have this, we are plotting this against this, right? So we can say that the intercept for this equation should be a negative intercept of -1, right? This should be the intercept of the equation, right? This should be the intercept, right? This should be the intercept. If this is the intercept, if this -1 is the intercept, we can say that our V, right? So a graph of magnification against the image distance with a negative intercept is supposed to yield a slope of 1/f, right? 1/f. Now, we can equate our slope, the value of the slope we will have, the value of the slope to 1/f, and then we have to indicate what this means. So this will help us to find the focal length of this particular converging lens, right? When we plot our graph and then do our little theory, we can say that our slope equals to 1/f, right? Then we can make our f the subject, and then we can find our focal length. Thank you.